Today I want to present my work, which has a title Genome Compression using Program Synthesis. I am Maletsky Denis, and my supervisor is Shumatsky Volodymyr Mikhailovich. I want to start by the introduction, why the genome compression is important, right? Because nowadays we decode the DNA sequences much more faster and much more better. Therefore, we accumulate vast amounts of genomic data, and efficiently storing and managing this data becomes a challenge. Today I want to show that using the concept of program synthesis, it can reveal a new message for the compression of genome data. Usually, when we define the problem statement, right, we choose, when we speak about the compression, we choose which criteria we want to maximize, whether we want to maximize the storage efficiency or the speed of the compression. Today, I'll try to maximize both criteria at the same time, or at least optimize them, right, compared to the other algorithms. And firstly, to start, let's look at the data we work with, right? The DNA sequence that we work with is basically a computer file that contains a long string, and that string contains the characters out of this alphabet of 5 characters. Those blue ones, 4 characters, represent the primarily composed of 4 nucleotides, and the last one, N, encodes basically it's a marker or like placeholder for badly decoded nucleotides. So it's just a placeholder that tells that there should be nucleotide, but we're not sure which one exactly. Okay, so we have 5 characters to encode. When we speak about compression, we start by calculating the so-called Shannon's entropy of the data, right? This is kind of like theoretical limit for the compression we can achieve, but that's important constraint in Shannon's entropy theory, right? Shannon tries to encode each character individually. Therefore, I want to show in this work that if we look at the whole sequence of the data, we can find a better compression rather than the one limited by the entropy of the data. To better illustrate this, let's consider this simple string, or you may call it a genome, right? Because it contains of 2 nucleotides A and C and has length of 16, right? When we calculate the entropy of this data, we'll get 1, which means that we need at least 1 bit to encode each character individually. And that's exactly what algorithm like Huffman would produce in this case, 16 bits that has one-to-one mapping to the original data, right? But I want to show that if we will try to look at the data from a different perspective, specifically for perspective of program that reproduces this data, right? We can try to find a shorter representation of this data. So if we try to look at the program, we can rewrite this program under the constraints of the program synthesis, right? And find a shorter one that reproduces the same data. For example, if we add also multiplication. And we can even modify the syntax a bit to make it even shorter, right? To move multiplication out of the parentheses. And then we can use something like reverse Polish notation to represent the same program and later encode this program using another algorithm like Huffman, right? In this case, if we use Huffman, we will get 12 bits that will represent our initial data, which will gives us 0.75 bits per character of the initial data, which is less than the entropy of the original data. So as we see, we can outperform the entropy, and that's the core idea of this work. So proposed algorithm composed of 3 stages. First one will divide the original genome into chunks of data, specifically into 16 byte long chunks, and encode each chunk of those individually, try to find the optimal program for each of those chunks. And to try to find those programs, we would use another work which is called EGG or EGG, which is known for a process known as a equality iteration, right? This process will drastically reduce the search space of the program by combining similar functions together. For example, here you can see that multiplication by 2 and bit shift by 1 is combined together, therefore reducing a lot numbers of loops in the search tree, right? And the final stage would be taking those optimal or suboptimal programs and encode them using another algorithms. In our case, we used Huffman encoding to get final bit stream that we can later write to the file. Also, today I want to present second algorithm, alternative to the program synthesis, which is a custom packing for the genome data. It has constant 3x compression, but it maintained the crucial feature of 0-1 random access. This implies that it can be compressed and decompressed in a constant time, and this 0-1 random access almost by definition makes this algorithm so-called embarrassingly, or you might say perfectly parallel, right? Which will gives huge performance benefits, right? And how these algorithms actually work, how we get 3x compression, is by taking 3 sequential nucleotides and compress them into 1 byte, and encode them into 1 byte. So to remember, we have 5 possible states for the character, right? And we will mark n as a special character, and will try to count how many n's are present out of these 3 nucleotides that we have. And we reserve first 2 bits into a byte where we encode the data to tell us how many n's are in those 3 nucleotides. And for example, let's look at 2 corner cases, right? When we don't have n, right? And counter for n is equal to 0. Then 6 bits will be used to encode the rest 3 nucleotides, 2 bits per character. Super simple. And again, if we have 3n, that's again simple. We don't need, we can just ignore the rest of the bits and just output 3n, right? In case when we have n equal to 1 or 2, it's a bit difficult. In these situations, we need, for example, here we need to encode the index of the n out of 3 characters, and later just encode other 2 nucleotides. And in case of n equal 2, we'll encode index of non-n character, right? And then encode that character. Okay, super simple, huge performance benefits. And I want to mention also that the compression of this data does not require any external data. It does not require any decoding tree, decoding table, or dictionary whatsoever. All the information that is needed for the decompression is stored inside the byte itself. That is crucial for the performance, right? And we can compare the compression ratio between different algorithms, for example, with Huffman encoding or run-length encoding, and our custom packaging and program synthesis together with Huffman. We can see that program synthesis with Huffman gives the best compression ratio and the best code length, which is strongly connected metrics, right? But unfortunately, we didn't bit the entropy of the data, and we will leave this for the future investigation, because I'm pretty confident that we can bit the entropy or come at least close to the entropy of the data by using program synthesis, maybe with another encoding algorithm like arithmetic encoder or something like that, for a better compression ratio. Thank you for your time. Hope you enjoyed this presentation, and hope you have some questions to ask. Thank you and goodbye.